So, we did that yesterday. It's the same as all the other nucleophilic attacks. This guy, sorry, caffeine doesn't help with this thing, but also it helps with this thing. So I think it's better for all of us if we have that. This nucleophile attacks the electrophile there, and we end up with this, which is really synthetically useful because we started with an aldehyde or ketone, and now we've got some things that can do some things, right? We've got an alcohol, which those can do a couple things, right? Not a ton of things. I want to say you can turn an alcohol into like a halide, right? Does that sound right? Yes, no? Okay, cool. I haven't sat in a Gen Chem 1 lecture in a lot of years. I taught Gen Chem 2, or Gen Chem, organic, whatever. I taught the second semester of this last year, and I did a brief skim of the first semester concepts-ish, and yeah, I don't remember a ton about first semester, so not off the top of my head. So you can do a couple things with an alcohol, but you can definitely do things with your nitrile group here, right? C triple bonded to N, you got all these pi electrons, and you got a nitrogen, which can have different, like, it can do a bunch of resonance things because it can have lone pairs, or it can do like multiple bonds, right? And it can go back and forth, kind of like oxygen does. Whereas carbon, I mean, you can do that, but you need to have somebody else there, like nitrogen or oxygen, right? Because somebody has to provide like the lone pairs. Carbon only comes with one for each bond, so. So we can do all sorts of chemistry with that. And in fact, you can, just with this, you can use an acid catalyst and just straight up get rid of this alcohol and turn it into a double bond. So that, and you know, it's easier to see, let me do this, so I'm gonna draw that, because I don't like looking at it like that. All right, 1, 2, 3. Yeah, we've got this. An acid catalyst is going to give us H, C, H, and that's linear, so that. And that is helpful. Yeah? Just when I look at that, it's really easy for me to start trying to figure out why one of the carbons has 5 bonds when it doesn't. It's just, there's a triple bonded carbon right next to a double bonded carbon, and they're all kind of, when there's not lines, I don't know, stuff blends together. You can take this same thing and you can reduce it to a primary amine by putting nickel in there and just putting a bunch of H2 gas over it, which honestly I always pictured as like, okay, yeah, that's how we learn it in organic chemistry, like in class. But how do you even do that? That would be really annoying. Yeah, apparently it's not actually that annoying. You can take like a pressure flask or a Schlinklein setup, but a pressure flask is even easier. And you just like hook up your gas cylinder to a pressure flask and you get everything ready to go, and then you just, you know, you'll have an outlet. Preferably that'll be like in a fume hood that has nothing flammable anywhere near it, because you're letting out the other gas, but you're also going to be letting out an amount of hydrogen gas, which is really flammable. just sort of put it under pressure with hydrogen gas and then seal that off and stir it for a while and it's fine. So apparently that's not all that difficult. Will that go? Is this question lying to you, or this reaction lying to you or not? Hands up for this is a true reaction and it is not lying to me. Hands up for I pick false, this reaction is lying to me. Is a dirty stinking liar. Yeah, because why?
It's an acidic solution.
Yeah, you've got a Grignard killer right there. That guy kills this guy, and don't consider it like.
What if it said you have 2 moles of Grignard reagent?
If it was very specifically said you have 2 moles, 2 molar equivalents, and your advisor is okay with you wasting money, then you're allowed to do it. Deal?
Deal.
All right. It has to specify how many moles you have, and also specify that your advisor is okay with you just throwing money out the window. Then you can do that. In which case you would need how many moles to make the reaction go? 2, right? And I mean, then we go, oh right, well, 2 in class, and then when we get to lab, we find a protocol that was somewhere, and they probably use excess Grignard reagent anyway, so then we probably use 2.5 or so, however much excess whoever published it last used, honestly. But yeah. What do you guys think? This is an interesting one. So, we really haven't talked about this. So, how would we approach this? Well, one equivalent of Grignard reagent. So, our nucleophile is a Grignard reagent. It's not changing. So, what are the 2 things we're comparing? Our electrophiles, right? So, I guess we're asking which carbon is a better electrophile. Which carbon has less electron density around it. So, what do we think?
A.
Yes.
Would it be A because it's more reactive?
So A is definitely more reactive than B, yes. So, yeah, I was looking at these, but these are numbered. Yes, A is gonna be a better electrophile, and so, yeah, you're probably gonna get reactions at both of these because, like, organic chemistry is messy and all sorts of stuff happens. And man, good luck separating all of those different products that you get on a column because columns are terrible. But yeah, so A is gonna react a bit better. So you're gonna have more addition here, but you can't stop it from adding here. Yeah. Yeah? Does that make sense?
Is it like when we say more reactive, is that because it's like less sterically hindered? Or
It's better. Well, it is.
Is it B and H?
I want to
versus
say it's
CH3?
it's less sterically hindered, but actually these guys are flat, right? So there's a whole unobstructed plane above and below that it can attack from on either one.
Even though there's a like the methyl group. coming
Yeah,
out of it?
because I mean it's
Yeah, I'd be pointing away.
still this one carbon is. I mean I think you're not wrong. I think one could argue that there's some level of steric. This is slightly less sterically hindered than this, and if this had like a tert butyl over here, then I would be like, absolutely, that's probably all over the place trying to be in the way. I think a combination of maybe that and also just this guy has a nice equal bond with a carbon, and this guy's got a very one-sided bond with a tiny little proton and not even a whole atom, just a little guy. I mean a whole atom, but like only technically. Yeah? Cool. gonna skip some of these guys, so we really do need to get going on this. And I don't know, if I have it on the schedule that Monday we're gonna finish this chapter and start the next one, I'm probably lying to you. We're probably just gonna hopefully finish this chapter. I tried to be less optimistic when I made this schedule. Last year I was very optimistic when I made the schedule. But this year we're gonna teach faster, and also I was less hopeful, more realistic, at least slightly. Okay, so, Wittig reaction. This is a method for synthesis of alkenes from aldehydes and ketones. So, we take a CO double bond, and we use this garbage, and we turn it into a CC double bond. This is a phosphonium ylide. So, if we get to the carbon-carbon coupling chapter, and if we talk about ligands there, or if you ever do like a bunch of carbon-carbon coupling chemistry, just, you know, use platinum or palladium to catalyze most things, and there's a bunch of carbons you can just make stick to each other because of catalytic coupling now. If you do that at some point, you'll recognize this guy. So that's a phosphorus with 3 phenyl rings coming off, PBH3. It's just a very bulky, it's a nice little ligand. It's got a whole lot of electrons, and then it's got one specific one lone pair. Does a nice little complexing of metals, no, not a lone pair. No, phosphorus has a nice empty. Don't worry about it. Don't worry about what it is on its own. I've never actually drawn one on its own, and I was thinking about how it might complex metals, but I don't actually do metal chemistry, so I was trying to do that off the top of my head. Anyway, here, it doesn't matter if it can complex metals, because what we have is we have a bond between the phosphorus and the carbon. The carbon is more electronegative. Is that true? Let me get a periodic table real quick and make sure that that's true. Where's my mouse? Okay. So, copper and phosphorus are in that nice little place where, you know, the closer it is up or over, it's more electronegative, the closer it is to fluorine. And these guys are these pairs, this type of diagonal, which is like, I don't know. So it's not so much electronegativity, but this guy, it's got an S1 shell, an S2 shell, and a P2 shell, right? Those are all the electrons it's got. The phosphorus has S1, S2, S1, S2, P2, S3, P3. So it's just sort of bigger, and honestly, when you get down here, bigger atoms are going to be more ionizable. It's easier to make their electrons kind of floof around. They're not holding on to them quite as strongly. Yes, floof around. That is a technical term. Hopefully this kind of language is helpful for understanding organic chemistry. Like, because I'm not trying to use this kind of language, this just happens, but also hopefully it's not an active hindrance to learning this. So we've got this going on. These phenyl groups are all electron withdrawing, so they're taking electrons away, or electron density away from the phosphorus, and we've got a, yeah, basically it's like a sort of a double bond between the phosphorus and the carbon, because we've got a negatively charged carbon here. It's just that in order to make that double bond, you have to use the d orbitals and break the octet rule for the phosphorus, so like, you can resonance that, but really it just sort of looks like this. And you've got a negatively charged carbon. So, this takes place under mild conditions, which is always nice, because there are all sorts of times that I look up a synthesis of something and I'm like, yeah, this will totally be easy to do. Let me just look up the STS of this thing real quick. Oh, nope, I don't want to play with tin. Or like, oh, well, fine, I'll do it, but obviously my undergrad can't do this, or my high school student, so I have to come up with a new project for them, because they are not touching this stuff. So, mild conditions, really nice thing for organic chemistry, like really super nice, yes.
Do we need to know how to make ELACs?
No. Okay. The only part of knowing how to make this thing that you need to know is you start with a PPH3 that's going to need a counter ion bonded to a CH3, and then you just get really aggressive to deprotonate it. So organolithium, real aggressive because we're trying to deprotonate a carbon, and that's the only part of this that like maybe you should know.
So we need to know the salt and that you're going to treat it with a base.
Just know, oh, you don't have to know like what the counter ion is, just know that like you start out with everything but the hydrogen is there, and then you use aggressiveness like a butyllithium static to deprotonate that carbon, and then you get that guy.
Okay.
Is that fair?
Yeah.
Okay, cool. Yeah, because that's the part of it I care about. I don't know that I'd actually test you on that, but just in case, I feel like that's fair enough to know. In order to make this, you deprotonate a carbon, and to do that, you get real aggressive. This is a fun mechanism to do, so we're going to do that when we come back. And I know there are a lot of hidden slides in this, but there are 54 slides. We are on 8 of 54, so in a way we're starting chapter 19 on Monday, I don't think. We're just gonna be fun. Yeah, take a break.